This is my demo of evaluating a modified cocaine noodles attack against the Whisper base and Turbo large models. There are two iterations of samples, one constructed with a gray box level of knowledge of the model being attacked, the other with a black box level of knowledge. I will now play a random handful of samples from each group and show the transcription of the sample afterwards. As you can tell, the gray box samples are much more effectively obfuscated than the black box samples. The statistics under each sample represent the word error rate achieved by human transcribers in a small study and the best word error rate achieved by the tested ASR models. To briefly understand why a gray box level of knowledge results in more effectively distorted samples, let's have a look at the sample distortion script used. Here is the script for generating the perturbed audio files written in MATLAB. So, briefly, under a black box level of knowledge, all four of these variables must be tweaked individually through trial and error in an attempt to balance distortion and ASR model accuracy. Under a gray box level of knowledge, however, only the amount of MEL coefficients returned, as represented by this variable here, is needed to be tweaked. This means that this becomes a much more straightforward minimization process, as the rest of these three variables are fixed throughout this process, and therefore results in more effective samples.
Hi, my name is Joseph Hall, and I've been working with Shishir Nagaraja, my supervisor, on testing the robustness of the real-world safety classifier for the game Roblox. Roblox is an online game with a young target audience with a voice chat available to those over the age of 13. There's two classifiers published, which were both tested as they have different training data and different architectures. To test both the classifiers, 6 attacks were used, 2 of which were black box attacks and 4 of which were white box attacks, coming from attacks used on speaker identification and automatic speech recognition models. The attack plane is fairly simple. Roblox uses ad hoc moderation, so an attack could use a short, unperturbed audio of 15 seconds, being played into the game environment, which would be broadcasted to all players in the game environment. However, shortly after, it would be flagged as unsafe and they'd be banned. By the attacker perturbing the audio, they can play longer messages, which could lure users off-site. We've already seen this being used in the text classifier, and it recently made the news for concerns around the safety of the text classifier. To benchmark the models and the performance of attacks, we needed to create a new dataset to benchmark the Roblox safety classifier. This is due to a lot of moderation data sets being focused on text, and some of the limited available English datasets for audio specifically were of single word utterances, so did not contain context or other features that would be included in more natural speech. The new dataset was created using Polias as a baseline, which contains YouTube video IDs and transcripts. We filtered the transcripts to those containing profanity and then used the library YouTube DL to download the audio from YouTube. Each attack was then applied to samples and the resulting label and noise level collected To aid with understanding labels, a safety metric was created. For the version 1 classifier, there was a no violation label, so we simply took that. However, in V2, they dropped that label, so we had to take the sum of the labels and subtract them from 1 to try get a safety metric to help compare between the two models. We did a distribution analysis of different words that we had filtered for in transcripts. We found that softer profanity came up more often. This is likely because this is considered more acceptable in general society. However, we still consider these profane as the audience is of a younger audience. So this would still not be allowed on the target system. We did the results looking at by label. For the version 1 classifier, there was a lot of variance across all labels, both positive and negative, mainly tending to be more negative, which means the content tends to be more unsafe after perturbation than safe. While you can target the white box attacks, we left it untargeted to see which way it would be more likely to go. So it was really interesting to see that a lot of these white box attacks made the content be detected as more unsafe than safe. For the version 2 classifier, there was a lot more tight distribution of how the labels were affected, seeing kind of more banding in particularly discrimination and sexual label, where profanity there is again a bit more variance. The black box attacks were less effective to an extent in V2 for specific labels, and the white boxes tend to still be effective, especially VMI FGSM. Looking at the results by the difference made to the safety metric, which we previously discussed, we found that there's both positive and negative changes to the difference in safety confidence. A negative value means that the safety confidence was reduced, hence the content would be considered more unsafe and more likely to be flagged. We see that there's much more variance in terms of the maximum change and the minimal change in the V2 classifier. However, this could be due to the way that we calculate this artificial safety confidence metric. When we look at the distribution of what is safe and unsafe, we find that the iterative white box attacks, especially in the version 1 classifier, are able to make all the content that was unsafe and considered safe, considered fully unsafe, where we see FGSM, which is non-iterative, see an increase in the number of samples marked safe as opposed to unsafe, and both our black box attack, being DFT and McAdams, reduce the number of samples marked unsafe. Particularly, DFT was very successful. In the V2 classifier, we see a lot more samples being marked safe rather than unsafe, with VMI FGSM having a distribution very similar to the original. However, the rest tend to significantly reduce the proportion of samples considered unsafe and make them considered safe. This is a demonstration of the audio attacks. I will start by playing a quick bit of the clean audio.
I think there's something that the co-idiots of this...
As you can tell, it's quite clear. Moving on, we'll start with DFT attack, which is a black box attack, which works by converting the audio to a discrete Fourier transformation version, and then thresholding frequencies in the transform that are below a desired magnitude. For the strongest version, we use 0.2. It's a very fast attack, and it sounds a bit like this. As you can tell, it's quite distorted, but that's at its most extreme. Moving on, there's the McAdam attack, which is another black box attack, which comes from the synthetic music generation domain, to add timbre to audio, and it sounds like this. As you can tell, it's quite clear, but the pitch has been distorted. Then we have our first white box attack, which is PGD, which is a white box attack that can be fairly slow due to the fact that it uses an iterative approach, as opposed to faster methods like FGSM we'll see later.
I think there's something that the cove idiots of this country don't understand. So cove idiots, listen up.
Next we have FGSM, which is the fastest of the group of attacks that use fast gradient sine method. It comes from originally the image domain and uses, and it sounds like this.
Cove idiots of this country don't understand. So cove idiots, listen up.
Then we have the momentum iterative version, which uses an iterative approach and a momentum factor to avoid local minima to make the attack more effective.
I think there's something that the cove idiots of this country don't understand. So cove idiots, listen up.
And finally, we have VMI FGSM, which is one of the slowest attacks to generate. This is because on top of having to create a momentum function, it uses the variance between points to make an even more effective attack sample. While we wait for that to run, some of the verbose statistics you may be interested in is the probability of safety, which is just a heuristic metric to compare labels more easily. And also there is this SNR, which is the level of noise in each sample. Finally, we've been able to get a output. As you can tell, it did take a lot longer than the other attacks, and it sounds like this.
I think there's something that the cove idiots of this country don't understand. So cove idiots, listen up. You realize that...
As you can tell, though, it was able to recover the most of its probability of safety compared to the other white box attacks. Where the others had a negative probability of safety, it was able to get its way back into the positive range. Obviously, this is a very extreme clip of audio, which was chosen to make it so the classifier would be able to classify it correctly very easily.